The input is a variable speed blower right here that when you change the percent input, it's going to increase or decrease the fan speed. That blows through this duct system, which has two heating elements, one here on the lower and then one upper. There's also an adjustable damper right here. For our experiments, it was left open the whole time. And then this is a temperature sensing element right here, which measures the temperature of the output. Couple system diagrams. The schematic at the top here. This is our input right here coming from the computer into the LabVIEW system. When you change the input, it's going to change the blower speed again, which we measured at the temp sensor we measured and put that back into the computer for our output. Block diagram. Again, input is blower percent power, and the output is in temperature per degree Celsius. This is a screenshot of the steady state from the LabVIEW system. This is circled right here because it's actually in minutes. So we're running, takes about 6 to 8 minutes to hit steady state. For this one, we're running at 50% input, and we're running both heaters on, so you get a lower and an upper on, and we're measuring temperature at the middle point. And right here, the damper's left open for the entire time. This is just a screenshot of an experiment. The input on this one is at 49.5%, and you're seeing a steady state output of around 56 degrees. This is our steady state operating curve graph for all of our inputs. You can tell we had some kind of variability down here, but the overall is negative 0.6 times the blower percent. So you're going to get for every 1% increase in blower, you're going to get a negative 0.6 times that degree change. Another screenshot from LabVIEW. This one is for the pulse response, or for the step response. For this one, we ran it for 18 minutes, so you get 6 minutes to reach the first steady state, and then it steps up for 6 minutes and steps back down for another 6 minutes. Again, both heaters on and measuring at the middle point. This is another example of one of our experiments. This experiment was run at 52% input, and then stepped up to 100%. You can tell there's an inverse response with our system. So as you increase the input, you get a decrease in output. This is a step down. You can tell we went from 100% input down to about 42%, and we saw a change in temperature increase about 9 degrees. This is our analysis of the step response. Right here is 63.2% of our output temperature, and when you get down here, the time constant is going to be from right here to right here, which on this graph is around 30 seconds. This is the analysis for our step down. Again, it's a 63.2% times the output range, which on this is about 51 to 43. It's about 8 degrees. And the time constant on this one, the step up, is a little longer. It's about 45 seconds. So the results of the step response, these were our middle inputs. We were looking for 50 to 52 degrees output here, and the high output was 52 to 54 degrees C. On the gain ups, for the step ups, are right here and right here. And you can tell you see a little more gain on the step ups than you do on the step downs. Results again for the step response. This is the time constant. Same thing. This is the middle output values and the high output values. Interestingly, they were identical for the time constant. There's it seems to be a lot of uncertainty on the step down responses. This is the FOPDT modeling of our step up on this one. You can tell on the input modeling, it's exact. So it's completely covering the output line, the actual line. And on the output, the red line is the actual value, and this other line is the model value. And we got pretty close. I mean, the model's pretty good coverage, where it's a little off right here on this slope. But we saw gain, based on the model, gain was about negative 0.19, and the time constant was about 30 seconds, which is pretty close to what we saw off of the step response. On the step down, same thing. On the inputs, it's perfectly covered, and then on the outputs, you're going to see a little variation right through here on the middle. And on the step down, we saw a gain of negative 0.18, and time constant was about 0.8 minutes, so 50 seconds, 45 seconds. And in conclusion, just summing up our results, for the steady state, we saw a slope of negative 0.6 times the input. On our step responses, the average time constant up was 28 seconds, and the average time constant down was 40 seconds. On the gains, we saw averages of negative 0.14 up and negative 0.13 down. And those are in degrees C per percent. And for the FOPDT modeling, we saw time constant up was 30 seconds, and when you compare that to step up on the step response, it's pretty close. It's off by 2 seconds. And on the down, we saw 48 seconds here on the modeling and 40 seconds here on the step response. So a little more variation there. And on the gain, same thing again. A little more variation on the gain between the FOPDT modeling and the step response. At this point, does anyone have any questions? Thank you.